What we want to do now is to relate some of these parameters describing our underdamped second order systems to the poles of that system. And this is going to become very important as we're looking at later units, particularly when we're looking at our root locus and designing with our root locus. So as a refresher, we had general expression for our poles for an underdamped response. And so I've written that again here. So this was shown in a previous video, but we have S1 and 2 are equal to negative zeta omega n plus or minus j times omega n times the square root of 1 minus zeta squared. And so of course, remember, that's where j is our imaginary number, the square root of -1. So we can look at this in our S-plane to get a better idea of what our poles actually look like. So we have a negative zeta omega n real part. So this distance here is negative zeta omega n. And then we have plus or minus j omega n times the square root of 1 minus zeta squared. So that would be our plus term, and then we have a minus term, j omega n square root of 1 minus zeta squared. And so what we can do is we can sort of draw out here our approximate pole locations. So let me move this a little bit, just so that's not getting cut off by that dashed line. So this distance here was our negative zeta omega n. And so basically we then have two poles, one here and one here. And we're keeping it general so that we can, of course, change this depending on the exact parameters. So another thing that we want to keep in mind that we showed earlier is when we were first introducing the idea of an underdamped response, we had an equation for the natural response. So we had C sub n for C natural. I don't think I used that notation earlier, but I've added this in. C natural response is equal to A times some exponential to the negative sigma d t cosine of omega d t minus phi. And so what we're going to do is we're going to relate a couple of these parameters as well to make things a little simpler in terms of evaluating changes in our parameters, peak time, rise time, or not rise time, peak time, settling time, and percent overshoot with regard to our pole position. Okay, so just kind of bear with me because we're bringing together several different ideas here. So first of all, we have this damped radian frequency, which was our omega d. So this omega d is our damped frequency of oscillation. So I misspoke a second ago, damped frequency of oscillation. And what we're going to do to make things a little simpler, we're going to say that this is actually equal to j omega d, and this is equal to, so this should have a negative sign, negative j omega d. So our omega d is equal to this omega n times square root of 1 minus zeta squared. And that's just making things a little cleaner. We also have that sigma sub d, which is our exponential damping frequency. And again, this is something we've mentioned before. So exponential damping frequency. And so for this one, we're going to say that this negative zeta omega n is equal to negative sigma d. And so that's how we can relate that to that previous equation. And again, this is going to make our life a little bit easier, as you'll see here in a minute. So now what we can do from trig is we can define a line. So let me do a different color. So we can define a line going from the origin to this pole, like this. And so of course that line is going to have some associated angle, theta. And so let's see if we can't figure out what the distance is and how that theta relates to our known parameters. So what we can do is we can use trig. Of course, we know that the length over here is this j omega, well, so let's ignore the j for a second. Let's just say this is omega n 1 minus r zeta squared. So that's the same because that's this height here. So we can find the length of this hypotenuse of our triangle because this is a right triangle. If we do square root of a squared plus b squared using this term and this term, what we'll see is that gives us omega n. So we can say that this distance here from the origin to the pole is omega n. Now, similarly, we can find the angle for our theta. So now that we know that distance of the hypotenuse, we can say that our cosine of theta is equal to adjacent over hypotenuse. Adjacent here is this negative zeta omega n, but we don't need to keep that negative sign because, again, we're sort of in this third quadrant here, or second quadrant rather. So we have the absolute value of that, which is omega n, zeta omega n divided by omega n. We see the omega n's cancel out. So what we have is that our cosine of theta is equal to our damping ratio zeta. Okay, so with some of these definitions we've written up here, we can sort of come back and we can simplify some of our equations for our peak time, our settling time, and our damping ratio. So let's go ahead and do that. So our peak time, the equation we previously had for that was pi divided by omega sub n square root of 1 minus zeta squared. Well, now remember, we just said that this omega sub n times square root of 1 minus zeta squared is actually just omega d. So we can substitute that in this equation to make it a little bit simpler. So pi over omega d. Okay, so now relating that to this plot here, we see that omega d is basically the distance, the vertical distance from the origin of our poles, either above or below. So what we can say then is if we're at a constant omega d, we have a horizontal line. So on that highlighted region right there, our omega d is the same. So what that means based on this equation then is that if we have a horizontal line in the s-plane, then we have a constant peak time. So horizontal line in our s-plane corresponds to constant peak time t sub p. And so that's through that argument right there that our omega d is basically the same at those horizontal lines. And we'll look at how it changes as we go further from the origin or closer to the origin here in a second. Similar thing we can do with our settling time. So for our settling time, our previous equation, we had approximated it as 4 over zeta omega sub n. Well, up here we said that omega sub n is equal to sigma d. So we can say this is approximately 4 over sigma d. And so let's keep in mind now, what does our sigma d represent? Well, our sigma d is representing how far we are away horizontally from our axis. So for a given vertical line, we would have the same sigma d. If we have the same sigma d, we have the same settling time. So what we have here then is that a vertical line or vertical lines, let's just keep it with line. So vertical line in our s-plane corresponds to a constant settling time. And so what I mean by a constant line, so for instance, if we have this highlighted line, we could shift our pole position. So maybe our pole moves to be down here, or maybe it moves to be up here. As long as it's on that vertical line, it's going to have the same settling time. And so we could be talking about poles for different for different functions. As long as they're on that same vertical line, they'll have the same settling time. So finally, we can talk about our damping ratio, which we said is equal to cosine of theta. And so what this tells us is that radial lines with the same angle theta are going to have the same damping ratio. So radial lines in our s-plane are constant damping ratio, and that also means that they're going to be constant percent overshoot. Because remember, those two are related and only depend on one another. So what we can do now is we can draw, let's get another s-plane here, and let's draw a couple different cases for different TPs, different TSs, and different percent overshoots and see how they change as we move in different directions. So let's do red. So let's say we have some horizontal line here that corresponds to some TP1. See if that'll clean up for me a little bit. There we go. So this is our TP1. And so remember, horizontal lines correspond to constant TP. So now let's say that horizontal line moves further away from the origin. So let's say we have some TP2 that's here. In that case, we could say that our TP1 is greater, our peak time TP1 is greater than TP2. And so the reason is, of course, as we're getting to larger, further away from the origin, this omega d is increasing. As that increases, our TP is decreasing. So that's why we say our TP2 is less than TP1. Okay, so second one, let's look at our settling time. So settling time is constant for vertical lines. So we could have poles anywhere along this vertical line here. And so let's call this, do that a little better. Let's call this our TS1. And so we can consider a second vertical line, TS2 here. And so in this case, we could say that our settling time TS1 is greater than TS2. And so basically what we're seeing is that the further away from the origin we are, the quicker our response is going to be. So, and we've talked about this a little bit with our first order systems, but again, the basic idea that the further left we are with our TS, the larger this value is, which means that our TS is going to be decreasing. So finally, let's look at our percent overshoot. So remember, percent overshoot is going to be constant for radial lines. So let's say we have one radial line here, which is percent overshoot 1, and one radial line here, which is percent overshoot 2. Okay, so this one's not quite as easy to follow, but let's sort of step through it. So from 1 to 2, we have a larger theta. And so remember, our theta is related to our zeta through this relationship here. So as theta is getting larger, our cosine of theta is getting smaller. So that means our zeta is getting smaller. And so if we have a smaller zeta, so that's less damping, that means we're going to have a larger percent overshoot. So what we can say then is that our percent overshoot 1 is going to be less than our percent overshoot 2. And so in the textbook, there are some good plots with a little more detail, and those are on page 152 in the 8th edition textbook. And what these plots show are basically different simulations of functions where, for instance, the poles are all on this vertical line. And so, of course, that would be switching our horizontal. It's showing for where poles are all on this horizontal line or for where poles are all on this radial line. So that might give you some good insight into that as well. But again, keep in mind, we're going to come back to this a lot, especially when we're dealing with our root locus. So if you have any questions about how we can relate our pole location to these variables and these parameters we talked about previously, definitely let me know and we'll get everything straightened out.